Hello, welcome back to another episode of Stats with Mats. I'm really going to miss these when we're done. No, just kidding. I won't miss these at all. But I am proud of what we've been able to accomplish in the online environment, and I'm feeling pretty good about your comprehension of statistics and your comprehension of applied statistics, most specifically. Today is the last topic we're going to do, multivariate regression with categorical independent variables. So that's the topic for today. That's what will be evaluated on this homework. And then we just have a final to take care of, earn all our points, and we can all go home. Well, not really go home because that's where we all already are. This is, I guess, my last opportunity to give you some dumb movie commentary. But maybe this one isn't dumb because this is, I am convinced that the thought I've stumbled into here is, at least to me, the most interesting philosophical idea I've ever had about movies, perhaps ever in my life. And what it deals with is, how do I want to put this? Where do certain works of fiction exist within other works of fiction? And the reason why I ask this question is because when I was flipping channels somewhat recently, I stumbled across a movie I really enjoy, Raiders of the Lost Ark, the first Indiana Jones movie. And then when that went to commercial, I started flipping channels again, and I stumbled across the original Star Wars. And I said to myself, it's a Harrison Ford night on cable. Two of his most famous roles, Han Solo and Indiana Jones. And then I started to think, seeing how that's the same actor, do the Star Wars movies exist in the Indiana Jones universe? So put another way, could Professor Indiana Jones go to the video store and rent Star Wars? Is that Harrison Ford? Does Harrison Ford even exist? Something to think about. Anyway, let's get into multivariate regression here. So in the way of review, last time I lectured about regression to you, I explained that the typical interpretation when you are dealing with an interval level independent variable is as follows. A 1 unit increase in X is associated with a B unit change in Y net of other effects, although we only interpret net of other effects if there are actually other effects. So we can omit that if and when we are doing a bivariate regression problem. But if we are doing a multivariate regression equation, we have to account for the fact that the other variables are assumed to be held at their means, creating the net of other effects situation for the estimation of each X's associated B coefficient. Make sense so far? I hope so. So looking at the rest of the equation, y equals bx plus a plus e, a is the value of y when x equals 0. It is the y-intercept, and it acts as a baseline for those 1 unit changes in x. P-value, we only have to interpret coefficients that are associated with a p-value less than 0.05. So think of that like your alpha level. If you see a value in the p column that is greater than 0.05, the correct interpretation is actually that x and y do not have a significant relationship. But if we see a value less than 0.05, and especially if we see that value of 0.000 within the p-value column, it is significant, and we can then interpret it using this 1 unit increase in x. And the r squared value, that is the amount of variation in y that is explained through your independent variables. Okay, so that's all. None of that is new. We've all done all of that stuff before. What if we wanted to deal with categorical independent variables? So I was kind of previewing this a little bit by saying, okay, education and income, that's a very clear bivariate interval level regression problem. But what about sex? That was the other example that I always threw in there, and I never quite went to say that, hey, sex is not an intervally measured variable. It's just a nominal difference in type, not amount. So we don't really have a unit to increase here. Let's say I go into the GSS and I look at that sex variable, and I see that males are coded as 1 and females are coded as 2. So a 1 unit change in sex is going from male to female, but the numbers there are only representing a type. 1 is different from 2 because 1 is referring to a different category than 2. It's not different in that, like, you can't say that females are 1 greater than males because 2 is numerically 1 greater than 1. That makes no sense. So there's not exactly an increase in a unit here. So what on earth are we going to do? Well, there actually is something that we can do here to give you a 1 unit increase. And so what I want to do here is introduce this concept. I think I've spoken about this a little bit before. I want to go into this a little bit more deeply because it's very important here. There is one number that more than any other number is very helpful to us in algebra. Once you get into calculus, then things like pi and e become really important. But when you're talking about algebra, the most important number that you can make use of is the number 0. Okay, so a dichotomous variable is a variable with 2 and only 2 outcomes. You may remember when we did t-test, I also introduced this as a dummy variable. Dummy variables and dichotomous variables are the exact same thing. The two ways of expressing the exact same concept. So a dichotomous variable has 2 and only 2 outcomes, and we're going to want to code those outcomes as 0 and 1. So if I wanted to include that sex variable from the General Social Survey in a regression, I would recode it as 0 and 1. It does not matter which group is coded as 0 and which group is coded as 1, but we have to make sure we include a 0 there. Here's why. Algebraically, 0s and 1s do pretty interesting stuff. So let's assume that we have y equals a plus bx plus e, and our x is that dichotomous indicator of sex, male and female. What happens when x equals 0? Well, that would mean that b is being multiplied by 0. And what happens when you multiply something by 0? It becomes 0. So when x equals 0, the slope coefficient is also 0. Conversely, what happens when x equals 1? Multiplying anything by 1 makes it itself. So when x equals 0, b equals 0. When x equals 1, b equals b. It equals itself. And so what that means then is by multiplying b by 1 and 0, depending on the case that, the particular observation's value, the coefficient, and when I say coefficient, I'm referring to b, the actual estimation, it becomes the effective membership in group 1 as compared to group 0. So let's say I was doing a simple 3-variable equation here where I had income, education, and sex, right? Just to keep with the example that I've been using a bunch of times already. Then when x equals 0, it disappears. When x equals 1, it becomes itself. B, the coefficient, becomes itself. So that value is the effect of being in group 1 as compared to group 0. And for our income value, let's say that males equal 1 and females equal 0. It could be anything, but I'm just grabbing that as an example. Then the coefficient is how much more or less money males are making on average as compared to the reference group of females, okay? So hopefully that makes sense theoretically. If it doesn't, let's examine some regression problems and try to flesh this out a little bit more, because seeing it in action always helps me. Like getting my hands dirty with a model, with an equation, that always helps me understand the interpretation of the model a little bit. So the category here of X that's coded as 0, the term we have for that is the reference group. In order to appropriately interpret categorical predictors, categorical independent variables, that is, you must be told what the reference group is, because it's the coefficient is the value, on average, the difference in group 1 as compared to group 0. So we will always be comparing to that reference group, okay? I will repeat that because I guess I'm jumping ahead here. The coefficient is the effect of being in group 1 as compared to group 0. The usefulness of this should be obvious because we don't have units that are mathematically distinct when we're talking about sex, race, ethnicity, nationality, citizenship. All sorts of things cannot be mathematically quantified. But by just using the simple properties of 0 and 1, we can get a pretty darn cool value here. So if you see a positive coefficient, if the coefficient for that dummy variable that you include is positive, that means that group 1's values are on average greater. So if I include sex in a regression on income and the coefficient is positive, it means that group 1 is making more money than group 0. If I see a negative coefficient, it means that group 1's values are lower than group 0's values. To put this in our example, group 1 makes less money than group 0 on average. So, do you want to see this in action? Let's go on a magical regression adventure together. Here's the same dependent variable and 2 of the same independent variables that we regressed last time. I want to predict number of children. That is going to be Y. And I'm going to use, just to fit the baseline model here, age and education, 2 interval level predictors. Are they significant? Yes, they are. If you follow my cursor, you will see that the p-value of 0.000, that is a smaller number than 0.05. So education is a significant predictor of number of children. Age is a significant predictor of number of children. Let's get to work interpreting this just in the way of practice. I would look at that education coefficient and say, a 1-unit increase in years of education is associated with a 0.119 unit decrease in number of children, net of other effects. Now I ask you to try your hand at interpreting the age coefficient. Here's how I would interpret that. A 1-unit increase in respondents' age is associated with a 0.038 unit increase in number of children, net of other effects. Finally, the last thing you are expected to understand how to do with these tables, R-squared. What percentage of variation in number of children have we explained through the inclusion of X1 being education and X2 being respondent's age? I see an R-squared value of 0.2079, therefore 20.79% of all variation in Y is explained by the inclusion of X1 and X2. Or put another way, 20.79% of all variation in number of children is explained by their respondent's age and a respondent's education levels, net of other effects. Okay, nothing we haven't seen before, nothing too crazy. What if we added this a very simple dummy variable for sex? So you'll notice how this variable is called sex1. I had to recode this in Stata. It's actually one of my frustrations with a lot of data sets is they do not by default include the number 0. And we want to include the number 0. We have to include the number 0. So this is sex1 where I did not alter the variable at all. I just set males equal to 1 and females equal to 0. What's my reference group here? It's females. So the coefficient here is the value for males as compared to females. Is it significant? It is. I look at my p-value and I can see that this is less than 0.05. Is it positive or negative? It's negative. That means that the group I'm interested in here, males, has on average lower values for the dependent variable than the reference group of females. It's always compared to the reference group. So my interpretation here is as follows. Males have 0.223 fewer children than females, net of other effects. And you notice how my education and age variable, they have slightly different estimated values because the model got a little bit better, but they haven't changed all that much at all. Okay, so running through just one more time very quickly what we just did. I coded my dummy variable into a 1 and a 0 labeling strategy. And I am interpreting the value on average, the value of being in group 1 as compared to group 0. You cannot interpret this coefficient without referencing the group that it's being compared to, without mentioning the reference group. Okay, what else we got to do? Let's add another variable. I'm curious about the effect of marriage. You will remember that last time I put in age at first marriage, which limited my sample only to married people and caused me to lose several thousand respondents. Here, I'm not going to do that. I'm just curious, you either are currently married or you are not currently married. It's one or the other. So, first two things I look at. One, is this a significant predictor? It is. P-value less than 0.05. Is this positive or negative? It's positive. So the reference group here, I don't have this in my slide, I guess I should, but I coded this variable as follows. If you are married, that equals 1. If you are not currently married, that equals 0. So married respondents have 626, more children than married respondents, net of other effects. How do I know it's more rather than less than? It's a positive coefficient. So that tells me immediately that group 1 has greater values than group 0. Not too bad, right? So if you look at the value for sex, changed a little bit, but still significant, still negative. It went from 0.223 to 0.256. Very minor change. The relationship is still pretty much identical to what was observed, even if the value has shifted slightly. We're doing stepwise regression because I want you to see this one at a time, but typically a guy like me, when I try to publish, I just present my final complete regression model. And if I was going to insert variables one at a time, that would usually because I'm constructing a model where I want to include a time lag, right? Like if I'm doing things over time, then I don't insert variables until such a time when they would have actually occurred. Hopefully that makes sense. Okay, so to reiterate, married individuals have 0.626 more children than unmarried respondents, net of other effects. I'm just going to change that. That's supposed to say unmarried. Hey, wouldn't be me if it wasn't a dumb PowerPoint mistake. Okay. So what we've done so far is only interpret the categorical variables that can be divided into two groups. Yes or no, you are married or you're not married. You're male or you're female in this data set. So what's it going to be if we needed any other type of categorical variable, nominal or ordinal, in which we did not have two and only two variables? The output in the regression table will look a little different, but the interpretation will not substantively change. What group is coded as 0? That's your reference group, and all other options are then compared to that reference group. So here's what I threw in. I was curious about religious intensity, how religious you are. What does that affect childbearing behavior? So religious intensity, you will remember that's a variable I asked you to work with on your homework. All three here are compared to strong. It's got 4 outcomes: strong, not very strong, somewhat strong, and no religion at all. So let's take a look at the coefficients here. Notice how underneath the variable name, religious, RELITEN, it's religious intensity, I see 3 coefficients. If I have 4 categories here, I can only estimate 3 coefficients. I have to have something that's coded as 0 and something that becomes the reference group. If I were to include, let's say I made 4 dummy variables, 1 for strong, 1 for not very strong, 1 for somewhat strong, 1 for no religion, and included them all, the model would actually blow up. Like Stata would refuse to run that and would say, we cannot regress that variable because there is no variation at that point anymore. So there would be no reference group, and without a reference group, there's no coefficient. So not very strong, that value you see there, will be compared to strong. Somewhat strong will also be compared to strong. No religion will also be compared to strong. It is entirely up to you to determine what the reference group is. You can code the variable any way you so choose. But let's go and interpret these. First of all, are these 3 variables significant? A p-value of 0.014, a p-value of 0.032, and a p-value, what I love to see, 0.000. All 3 of these values are less than 0.05. Therefore, each one of these is a significant predictor of number of children beyond the 0.05 alpha with 95% confidence. Let's take a look at no religion first, because that's the most powerful coefficient. Those with no religion have 0.362 fewer children than those with strong religious intensity, net of other effects. What about somewhat strong? Different number, different category, same interpretation idea. Those with somewhat strong religious feelings have 0.163 fewer children than those with strong religious intensity, net of other effects. And then finally, those with not very strong religious intensity have 0.128 fewer children than those with strong religious intensity, net of other effects. If you look at some of my articles, you will see I do this somewhat frequently with the European Social Survey, which asks people, relative to other people in your country, how financially well off are you? Like how would you describe your income relative to others in your country? It's pretty much the only way to get a measure of national level social class across a continent that has a bunch of countries, a ton of different currencies, a ton of different living standards, right? The median income in Switzerland is about $60,000. In Bulgaria, it's $6,000, and they're both in the same European continent. So, you could be doing well in Bulgaria, but be considered poor in Switzerland. What I do is I take those deciles, right? It goes from 1 to 10. And for 1, 2, and 3, I make that lower income. And 4, 5, 6, 7, I make that middle income, and 8, 9, 10, I make that upper income. And then I regress, and I always omit lower income as my reference group. And then upper income Europeans are compared to lower income Europeans. Middle income Europeans are compared to lower income Europeans. Not too bad, right? Can we do this with a categorical variable with even more categories? We sure can. Now, we haven't used Stata in a couple months, so I never got the chance this semester to answer the question that is always asked. It's like clockwork. At some point, somebody will come to me and say, why on earth did you want zodiac sign to be included in the class data set? Because this is not the whole general social survey. It's just a portion of it that I used for teaching examples. The reason why I included it and I wanted to use zodiac sign is because it's sometimes helpful for me to have a variable that I know is not going to be correlated with anything. Zodiac sign is not a significant predictor of anything. So let's take a look at what that looks like. Here is the regression model, and I've added in zodiac sign, and let's count them up. We have 12 zodiac signs out there, or so I'm told by astrologers when I watch TV at 2 in the morning. Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, Sagittarius, Capricorn, Aquarius, and Pisces. All right. Let's count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What's missing? If anybody out there is an Aries, you didn't hear yours get called. The way that this is coded is Aries is the reference group, but you could have made the reference group anything you wanted and it wouldn't have mattered. Nothing is going to make this significant. So this is, do people have more or fewer children depending on their zodiac sign? Let's start with Taurus for 2 reasons. 1, it's the first one that I see here, and 2, it's my zodiac sign. It's my zodiac sign. And so what's the appropriate interpretation of Taurus? Well, I can look at that coefficient and see 0.026162. I can say that Tauruses generally have very slightly more children than Aries. No, that's not the right answer. The right answer is that on average, Taurus respondents do not have a different number of children than Aries respondents, because look at my p-value. These are all well above 0.05. There's an 81.5% chance that you would have just gotten this through random sampling chance. Pisces is a 94.2% chance that you would just get this by random chance. But don't lose sight of the fact of what we did here. I threw in a variable because I wanted you to see what this would look like to interpret a non-significant coefficient. But I had a categorical variable with 12 categories, and that fit into the model just fine. Everything else was interpreted as being its effect as compared to the reference category. No more complicated than for sex and for whether somebody is married. No more complicated than religious intensity. It's just 11 different categories to look at. But I sort of knew going in that none of these would be a significant predictor of the dependent variable. So if we're running through this equation, you interpret age and sex, or age and education, pardon me, as you would any interval level variable. A 1 unit increase in X is associated with a B unit change in Y. I interpreted sex 1 and married as compared to the reference group of each variable. And then for religious intensity and zodiac, I interpret each one of those categories as compared to the one reference group set aside for that particular variable. So if I have a dummy variable, there's one reference group and one group that you're actually looking at for the coefficient. For anything with more than 2 categories, every individual category is compared to that one reference group, and you can set that to be whatever it is that you want to set it to. All right, so wrapping it up, categorical variables, they got to have a reference group. Each coefficient is then the effect of being in the group in question. The group coded as 1. as compared to that reference group. And in perhaps more exciting news, like I get very excited by regression and math, but I was a weird child. That's it for my new material, guys. There will be nothing new given to you from this point onward. We just got to wrap up with one final homework, something approximating a final exam, and we're done. Let me know if there are any questions on this. Keep up the good work. I will reiterate my willingness to be flexible with you guys as we finish this out. But I can only help people if I know that there's an issue. So stay in contact with me if you need me. I am here and I will take care of you. Thanks very much, and bye.